switch off your camera to save bandwidth. We also have a question and answer session after the talk. You can either post your questions in the chat or you can ask your questions live. Today is a special day because it marks the beginning of World Space Week. And just to give you some background on the event, World Space Week is an international celebration of science and technology and their contribution to the betterment of the human condition. The United Nations General Assembly declared in 1992 that World Space Week will be held each year from October the 4th to the 10th. These dates commemorate two special events. October the 4th, 1957, it was probably before a lot of our time. It was at least before my time. It was the launch of the first human-made Earth satellite, Sputnik 1, thus opening the way for space exploration. So an exciting time for space exploration. And on October the 10th, 1967, the signing of the Treaty on Principles Governing the Activities of States in the Exploration and Peaceful Uses of Outer Space, including the Moon and other celestial bodies. And of course, who better to invite than Professor Kavilan Moodley, who is an expert in astronomy and astrophysics. Professor Kavilan Moodley is currently a full professor in the School of Mathematics, Statistics and Computer Science and director of the Astrophysics Research Center at the University of KwaZulu-Natal. He completed his PhD in 2002 at the University of Cambridge, after which he worked as a postdoctoral researcher in astrophysics at the University of Oxford, before returning to South Africa in 2003 to take up an academic faculty position at UKZN. Kavilan's research interest is in the area of cosmology and involves confronting cosmological theories with observational data, in particular observations of the cosmic microwave background and large-scale structure. Kavilan served as a scientific board member of the International Atacama Cosmology Telescope Project, a member of the International Science Working Group for the Square Kilometre Array, SKA project, and an associate editor for the South African Journal of Science. In 2007, Kavilan won the South African Institute of Physics Jubilee Medal, a great honor to achieve. Kavilan has published over 100 research papers with over 8,000 citations, and I actually had a look, and I think it's now more than 10,000 citations, Kavi, and has delivered invited lectures at several international conferences, including the COSPAR Scientific Assembly in 2018. He's currently the principal investigator of the Hirax telescope project, which aims to measure the evolution of dark energy and localized fast radio bursts. Now, without further ado, I leave the stage to Professor Kavilan Moodley.
Thanks, Tanya, and thanks for that excellent introduction. I'm just going to share my screen with my presentation. Okay, Tanya, is that visible?
Yes, it is. Thanks, Kavilan.
Okay. Yes, welcome to everyone in the audience, and thank you for joining to listen to this talk. And yeah, it's a special occasion, as Tanya mentioned, the World Space Week. And this is also part of a series of public lectures, reaching out to the local and national kind of community to make people aware of what we do. So today, I guess I'm going to be telling you a story. We like telling stories, and I'll be telling you a story about the Hirax telescope, and also, but first to tell you a bit about what I do, and in particular, what we study in cosmology, and what we know of cosmology, and what we don't know in cosmology. So I'm based at the Astrophysics Research Center, and So in terms of, we've been telling stories for a long time. We've been looking up at the night sky and also telling stories for a long time. One of the more prominent set of objects in the night sky are the planets, and you can see them moving around. Each night when you look up at the night sky. One theme in this talk is structure in the universe, and immediately we encounter the structure in our solar system. We've got a large body, the sun, and the planets that kind of aggregate towards the sun or cluster around the sun. And we'll see this theme throughout the talk of clustering in the universe, where we have structures that form and have formed through, processes from very early in the universe. So in our solar system, and obviously, the dominant object is the sun, and that's what nurtures us. But what is the sun? Well, the sun is basically, thinking in terms of physical effects. It's a balance. It's a big ball of hydrogen gas, but it's really there because it's a balance of gravity and pressure. And these balancing forces are also responsible for much of the structure we see in the universe, which I'll be talking about in this talk. So gravity is trying to contract all this gas because gravity is attractive, and the pressure of the gas, like the pressure of the air in the room you're in, is the molecules or the atoms are kind of bouncing off each other and resisting this collapse. So really, the story about the sun is the story about a pressure-gravity balance. Eventually, so the sun also gets pressure from burning hydrogen to helium, and so through a process of nuclear fusion, it resists the collapse of gravity. Ultimately, that fuel will run out when all the hydrogen is burned up, and the sun will then start contracting and then expanding again, and it will eventually become a red giant and swallow the Earth. So you don't have to worry, that's not going to be for many more billion years. If we look at the solar system, the sun, is the dominant object in the solar system. But if we go further, the sun just blends into the background. It's just another star in a vast collection of stars. So here's a nice image of actually the Meerkat telescope in the Crew with the background, image of the Milky Way. And if you haven't done this before, I would encourage you to go to a dark place, either the Karoo or the Drakensberg, and look up at the night sky. The skies in South Africa are absolutely amazing, very clear, and you can, just see all this magnificent structure. So what we're looking at here is the center of our galaxy, which is called the Milky Way. And I'll zoom out and show you an image, not of our galaxy, but of similar galaxies, so you can understand the structure. And what you see is there's a lot of stars, but there's also dust, which is blocking the light. And you can see these dark patches, which are, mostly dust. And the stars are made up of gas, as I mentioned, hydrogen gas, that has collapsed into, into the spherical object. And the light being given off by these stars is what we're observing. And so if we zoom out further, and now we're in the realm of the galaxies, we see that in this middle image is basically an image of a spiral galaxy, which is similar, we believe, from what we infer, to our Milky Way galaxy. So we believe our galaxy, Milky Way galaxy, is a spiral galaxy with these beautiful spiral arms, and so those arms are caused by rotation within the galaxy. And at the center of the galaxy is a bunch of really old stars that are bright, whereas in the outskirts you actually see a lot more action going on. And these are regions where new stars are forming and giving rise to this kind of blue light and this bluish light, whereas these old stars have this kind of orange light. So these images are actually from the James Webb Space Telescope. It's an amazing facility that has been in the press, recently, since it's been launched. And so you see that galaxies don't just come in spiral shapes, they also come in elliptical shapes, which are just big bulges of gas, and they actually interact. We see a lot of galaxies interacting, and so here's some images of galaxies interacting. So our sun is just one star in our galaxy, which is made up of billions of stars. And our galaxy, the Milky Way, is just one galaxy in the universe where there's hundreds of billions of galaxies. So the universe is vast and contains a lot of this matter, and we'd like to understand that. So if we zoom out even further, and now what I'm showing you is a map of the galaxies, and this is from the Sloan Digital Sky Survey. So each dot here is actually a galaxy. So, and it's kind of color coded according to the density of or mass of galaxy. And what you see is that, well, there's millions, millions of galaxies here. And the structure that we see, again, we come back to the theme of structure in the universe. You see that galaxies don't just randomly live or exist in the universe. They come in kind of groupings. And so you see things like what we call, filaments of galaxies, even sheets of galaxies. So there's this overall order or structure in the universe as we zoom out, to the furthest extent. And so if we go out to the biggest, and this is a lovely image showing, going in orders of magnitude from, the solar system all the way out to the nearest galaxies, and then to the furthest galaxies away, and finally to the, the edge of the universe, where the furthest thing we can see is the cosmic microwave background, which is the leftover heat from the Big Bang, which I'll talk about shortly. So this is going to the furthest visible edge of the universe. It's where telescopes like the James Webb Space Telescope are taking us. So how do we understand all of the structure in the universe, how the universe originated, what it contains, how it is evolving? And so the one essential ingredient is to understand gravity. And I've mentioned gravity already. And what's key is this Einstein's theory of general relativity, which says that gravity actually curves, the space and time. So matter in the universe, the action exerts a gravitational force by curving space and time, and then objects that move past move in this curved space-time. So actually, with that theory of relativity, we can now build a model of the universe, taking this idea of the curvature of space-time into account. And analogy here is, if you have a rubber sheet and you put a heavy metal ball, that ball will curve the rubber sheet. And if you now roll a marble across that, it will not move in a straight line, but it will move along a curved path. And that's how Einstein and we understand gravity today. So we can build this model, and we make some simple assumptions which actually take us very far. We assume that there's a high degree of symmetry in the universe. The universe is basically uniform on the larger scales. And if we apply that symmetry, we come up with three possibilities for the geometry of the universe. Either it's this flat geometry, it's a curved geometry like a sphere, or it's a saddle-like geometry. And what we actually find from observations, and I'll give you the answer, up front, is that the universe is actually very close to flat on the scale we can observe it. So this kind of Euclidean geometry that we all used to on Earth is very applicable. We can then take this model and apply it to understand the universe. One thing we discovered, and this was Hubble, was that the galaxies, so Hubble did this by mapping out the nearest galaxies to Earth, and through a careful process of measuring their velocities using an effect called the Doppler effect, similar to if you have a siren from an ambulance and ambulance goes past, you hear the pitch of that sound changing. And so it's a similar effect. And if galaxies are moving away from us, the light we receive from them actually gets shifted. So the kind of pitch of that light, so to speak, changes. And so we can measure velocities. And then Hubble established a program of measuring distances, and so to these galaxies. And so what he found was that the further away a galaxy, the faster it's moving away from us. And the only way one can explain this is either we assume that we live at the center of the universe, which, from history we've learned is not, is not a good assumption to make, that we're special in the universe, or that everything, has an equal footing in the universe, and that means that all galaxies are moving away from all other galaxies. And the way that can, the only way that can be possible is if the universe is expanding. So the analogy that is often used is, if you imagine a balloon and you put, stick on some buttons and you then blow up the balloon, then all the buttons on the balloon will move away from all the other buttons. And that is the idea of the expanding universe. in this case, the fabric of space-time is, that the material that comprises the balloon. So it's really the fabric of space-time that's growing. So if we have an expanding universe, that means if we go back in time, it was smaller and smaller and smaller. And so at some point in the past, and this is about 14 billion years ago, the universe would have been very tiny and would have kind of began or originated. And that's what's shown here, kind of in the left of the cartoon, is this big bang origin to the universe. So the universe began very hot and very small, and with time it grew and cooled down. And as it cooled, and I'll explain, we could form the light elements that we observe in the universe today, like hydrogen and helium and lithium. And then as it further cooled, and this is over a period of 14 billion years, the matter that existed in the universe could then form into planets and stars and galaxies. So that's the idea of the expanding universe. As I mentioned, the universe was hot in the beginning. And do we have evidence that it was hot? Yes, we do. We've measured in the 60s, we've measured the cosmic microwave background. So let me break down this name for you. Cosmic is because it's cosmological in origin. Microwaves is because that's the wavelength of the radiation. It's about as long as your microwave, so something like 30 centimeters. And background because it pervades the universe. It's all around us. If you think of this light in terms of light particles or so-called photons, then there are about 400 photons in every cubic centimeter in the universe, throughout the whole universe. So it really is, pervading the universe. If you switch on, well, back in the day, if you switched on your television and didn't tune your station, and the static that you observed there would roughly about 3 to 5% of that was coming from the cosmic microwave background. So we have detected this remnant heat from the Big Bang. And this gives us more evidence that the universe began in a Big Bang. And so shown here are successive images of the cosmic microwave background from the first observation by Penzias and Wilson, for which they obtained a Nobel Prize, to the follow-up observations of the anisotropy or irregularities in the cosmic microwave background by the COBE satellite, which again, this work received a Nobel Prize, to more recent measurements of these fluctuations by WMAP and the Planck satellite. So if our universe began hot, then it was hot enough at some point to actually break apart, if you're going back in time, to break apart the matter. So the energy in the universe, the light, was able to disintegrate or dissociate atoms and even nuclei. And so we would expect there to be a relic abundance of these light elements like hydrogen and helium and lithium in the universe. And that is exactly what we see. So this is another cornerstone of the Big Bang theory, that we have these primordial, or from the very early universe, we have these elements that exist in the universe today that we can measure, that are not formed in stars because they're easily destroyed in stars, but there is a relic abundance of these elements that we measure. For example, lithium is easily destroyed in stars, but we see lithium in the universe, and it could only have come from the Big Bang. So that's the kind of cornerstone. And so we can ask the question: how did this, how did the universe, as it cooled, form these galaxies? How did it form the structure in the universe that I alluded to? And we believe that basically the universe was very smooth and uniform, as I mentioned. That's kind of one of the assumptions in the model, cosmological model. But as it went forward in time, and this is a snapshot of a simulation showing the evolution of the universe from the earliest period, billions of years ago, to very recently. And what you can see is that because gravity is attractive, if there were small irregularities, very tiny irregularities, roughly of the order of 1 part in 100,000, so really, really small, then because gravity is attractive, these would grow in time. Basically, if there was a little more matter in one part of the universe, more matter would collect there because gravity is attractive. And eventually, this region would become the site of where a galaxy or a galaxy cluster or even a larger scale structure will form. And you can see this pattern that I've shown you already from the data. You can see we can reproduce this pattern in a computer. So that tells us that we understand how these cosmic structures, including galaxies and galaxy clusters, have formed. So the idea being that we have these small ripples in the very early universe. These ripples grow through the action of gravity and then form the structures we see today. And you could ask, do we see these ripples in the early universe? And yes, while these ripples existed in the matter, because the light was also caught up with the matter, we also see these ripples in the light. And this is an image of these ripples. This is 400,000 years after the Big Bang. So very, very early on, compared to 14 billion years of evolution. And you can see these ripples. These are exactly the same ripples that exist in the matter and have grown into the galaxies that we see today. So these ripples are actually really informative. They tell us that structure in the universe originated from small irregularities very early on in the universe. Of course, you could ask the question, where did these come from? And we can maybe discuss that in the question and answer session, because that's something we cosmologists are still trying to figure out. But if you take this pattern and you ask how much, how does this pattern differ compared to what we observe, and you build a model, you can build a very simple model based on sound waves. And I'm showing here something which is studied in a first-year physics class, which is a spring with a mass on it. So something called a harmonic oscillator. And here you've put that spring with a mass on it in a kind of gravitational well, or basically letting it act under the action of gravity. And you know that if you pull a spring, it kind of bobs about. And that's that bobbing, it kind of gives rise to these sound waves. And that's what we actually see, these ripples in the cosmic microwave background. So we have a good theory that can explain this pattern of anisotropies. We have to tweak some parameters in that theory, some numbers in that theory. And those numbers are actually really important in cosmology. Those numbers are the amount of matter in the universe, the amount of dark matter in the universe, the amount of something called dark energy. And so when we actually match the observations, the theory to these observations, we find that ordinary matter only makes up about 5% of the energy in the universe. Of the matter in the universe, there's a large component of dark matter, which makes up 27% of the energy in the universe. And the rest of the energy is something mysterious called dark energy. So you can see that, obviously ordinary matter we know very well. It's the stuff around you, that stars are made of, that planets are made of. And then beyond that, astronomers aren't very creative. They don't, they struggle to give names. So the matter that we believe exists, to support the rotation of galaxies, we call it dark matter. And the energy that is causing the universe to speed up in its expansion, we call dark energy. So, obviously need help with giving more appropriate names. But we can ask the question, what is this dark matter and what is this dark energy? And so this is just another cartoon showing how the stars and galaxies and dust and gas is only making up a very small fraction of the matter, 20%, and that matter itself is only making up a small fraction of the total energy. It's only making up 30%. So the dark energy dominates the energy content and the dark matter dominates the matter content of the universe. And these numbers we get from observations of the cosmic microwave background. So there's this cosmic agreement, and what I'm showing here is the density, the fraction of energy that's dark energy in the universe. 1 means 100%, and the fraction of energy that's in matter, and 1 means 100%. And so you've got all these observations from this cosmic microwave background, from clusters of galaxies, and from supernova, and I'll get to supernova next, that are pointing to a universe which is made up of 30% here. We read that off, 30% that's matter, and 70% that's dark energy. So we've kind of arrived at this cosmic agreement. But that doesn't tell us what are these mysterious things called dark matter and dark energy. And so the way we kind of stumbled onto dark energy, and we weren't expecting it. We were expecting a universe that was only made up of matter. 100% of it was matter. But this was through observations of these type 1a supernova. So these type 1a supernova are basically what we call standard candles. So they have a brightness that we can understand or model very accurately or calibrate very accurately. That's because they are basically explosions of white dwarfs. And when the mass of the white dwarf reaches a certain limit, 1.4 times the mass of the sun, then when it's collecting matter, then it basically explodes. So this type 1a supernova are very standard in that sense. And you can see that they're very bright. This is a supernova in another galaxy. Remember that a supernova is an explosion of a single star, and the galaxy is contains billions of stars. Sorry, there's someone who's unmuted. Yes, so the galaxy contains billions of stars. So you can see that a single star, when it explodes, it's quite an energetic event. It shines as bright as its host galaxy. So we can see these supernova very far away, which means that they were an excellent way of mapping out the distance and the geometry of the universe. And we could look very far out. And what you found is that if you mapped basically what Hubble did and you extended that to further distances and kind of further velocities, what you find is that the universe is actually not slowing down in its expansion, but actually speeding up. And that was a very counterintuitive discovery, which again, won the Nobel Prize recently. But it's now pointed the way for what we believe is, this accelerating universe. So coming back to this picture that I showed you earlier, we believe the universe originated, in a big bang. And what exactly happened in the very beginning, the details are unclear. We see after 400,000 years, the cosmic microwave background radiation. That's when matter and radiation, light separated. And then as matter collapsed and grew, the planets and galaxies formed. But then most recently, this dark energy has come to dominate the universe, and it's causing the universe not to slow down in its expansion. And you would expect it to slow down if it was only matter. For example, matter attracts. If you throw a ball up into the air, it would come back to the earth. But in fact, the universe is expanding. It's accelerating in its expansion. So it's growing faster and faster. So the question is, what is this dark energy? And so to put it all in kind of one slide, in the early universe, the light was dominant, then matter came to dominate thereafter. And that's the realm of the galaxies, when the galaxies form. And now dark energy dominates. And what it's actually doing is it's causing the universe and the contents to separate, at a faster and faster rate. Right. So we would like to understand what is this dark energy. And one possibility is something that Einstein actually introduced, soon after he developed his theory of general relativity, which is called the cosmological constant. I'm just checking my time. It's long time. So the cosmological constant he introduced because he realized when he came up with these the equations that model the universe, he realized that the universe actually would collapse. And he, from his, prejudice from looking out at the night sky and seeing everything as being unchanging, he felt that the universe should be static. And so he introduced this cosmological constant to repel gravity, so to fight against gravity. So it's kind of an anti-gravity or anti-tension. And that's why, it's causing this accelerated expansion of the universe. So the cosmological constant is something that is an energy in the universe that is both constant in time and in space. And so there are other options. For example, if we have a field, which is commonly used to describe, used in physical theories, we have a distribution of energy that maybe changes in time and possibly could change in space. Why wouldn't that work? And the answer is we actually haven't distinguish those two options. So there's a big program to try to understand this dark energy. Is it a cosmological constant, or is it something that's an energy that's changing in space and time? And so there's a number of large programs, billion-dollar projects or telescopes that are being built to actually answer this question. Satellite experiments, ground-based experiments. Some of you may have heard of the Rubin Observatory doing the legacy survey of space and time. Some of you may have heard of the Roman telescope, or Euclid, which is both satellite experiments, which will be measuring supernova. And so there are many ways to actually probe and understand if this cosmological constant, which has its stiffness has a number -1. So that's the ratio of its pressure to its density. So is it this cosmological constant right on this line? And observations are converging on that now. Or is it something else, that changes in time? And that's a big question. So there's a number of experiments that are trying to answer this question. And Hirax is one of those experiments that's trying to answer this question. So how are we going to do this? We're going to use a technique, and I'll go back here, called the BAO, and it's called the baryon acoustic oscillations. So these are basically, I mentioned that the light and matter were coupled, and they were like a spring, a mass on a spring. And this is when the spring is moving outwards, and that's the analogy is the light. It actually carries with it matter. And when they separated, that matter, it basically dumps it. So I'm just going to show you a movie. Sorry, my connection may not be the best, so it may be jumping a bit, but you can see this ring moving out. That's this ring of matter being carried by the radiation. And at some point, let me just pause it at the end. At some point, the radiation and matter separate, and this ring gets left behind in the universe. I'll just pause it there so you can see that ring. And as we move further, you can actually now, this ring will show up in the distribution of galaxies in the universe. And so that's what we call this baryon acoustic oscillations. Let me move to the next slide. So how do we measure these features? It's basically a slight overdense or slight excess of galaxies or dark matter on a very large scale, something like 500 million light years. So it's a very large scale. What we need to do is we need to map out the dark matter in the universe. A good way to do that is to measure all the galaxies in the universe. So I've shown you this image or something similar before. So this is an image, true data taken by the 2-degree field galaxy redshift survey. And then the previous image was actually taken by the Sloan Digital Sky Survey, and that's shown here. So you can see, as I mentioned before, all these structures. And these are actually simulations in red on the bottom, on the right and the bottom, that actually are meant to mimic these observations. So you can see that we've got this foamy, frothy structure in the distribution of galaxies. And if you go in and actually measure on a scale of this baryon acoustic BAO scale, you will find a slight excess of galaxies. And that's what is called this baryon acoustic oscillation. What this means is that you now have, and you can think of these as kind of rings of power. So if you go away from a central galaxy and you measure what's the excess of galaxies, you'll find there's a small excess on a scale which is very large. It's 500 million light years. So it's quite a large fraction of the volume in the universe. And so what you see is that these small kind of ripples, or these small rings that were left over in the early universe, grow and give us a slight excess of matter. And that's shown, and don't worry about the details of this, but basically this is real data from the Sloan survey, the BOSS survey. And what it shows is that there's a slight excess of galaxies on the scale, 150 megaparsecs, which is basically something like 450 million light years. And so you see there's a slightly more galaxies. What this now gives us is actually a standard, what is called a standard ruler. I mentioned the standard candle, like supernova. We know their brightness, so we can chart the expansion of the universe. Now we have a standard ruler. In a similar way, we can also chart the expansion of the universe because we've got something to measure it with. So this is something very special that we kind of, privileged to have. We've been given by nature this baryon acoustic scale that we can use as a ruler going back in time. Right, so instead of now using galaxies, the visible light from galaxies, we can also use the hydrogen gas in galaxies, because that hydrogen is the fuel of the stars, as I mentioned previously. So we can also use the hydrogen to trace out the galaxies. And shown here is a map of the hydrogen in a simulation. And you can see that it traces out the total gas in the galaxy. I'm sorry, in the large scale structure. And this frothy structure is exactly the same structure that we've seen in the large scale distribution of galaxies. So we can use hydrogen. How do we measure hydrogen? Well, you can measure it using a radio, using observations in the radio. And basically, a hydrogen atom is an electron going around a proton. It turns out that these protons and electrons also have a spin, so they'd like to spin in a certain direction. And if the proton and electron spins are in the same direction, it's a different amount of energy than if they were in the opposite direction. So if the electron flips, and it does so spontaneously, then it gives off that amount of energy through a light particle or a photon. And that photon has a wavelength of 21 centimeters, something very much the size of your microwave. So that, or larger. And so that photon actually, as it moves to us today, gets stretched by the expansion of the universe. And so we actually measure these photons or these light particles in the radio. So we can use a radio telescope to actually detect hydrogen in the universe. And we have made maps of individual galaxies, the hydrogen in individual galaxies, using telescopes like the Meerkat, for example. So this technique is useful. And in fact, we don't have to resolve the galaxies because, as I mentioned, the BAO, that scale, length scale is very large. So we can make actually a blurry map of the galaxies. And that helps because it means that we can use a telescope which doesn't have high resolution. Unlike Meerkat, which has very high resolution, we can build a telescope where the separation between the dishes is very small. And that's the idea behind, that's a concept for Hirax. Sorry, I'm just trying to change slides here. Okay, there we go. So how do we design a telescope, a dark energy telescope, to map out these baryon acoustic oscillations? So you see here is a map of the temperature of the hydrogen in the universe. It's so-called brightness temperature. It's very small. It's a thousandth of a degree Kelvin. And the issue we face in mapping out this signature or this temperature is that the galaxy that we live in is very bright. The galaxy is tens of Kelvin, so 10,000 times brighter than the signal. So we need to build a telescope that is very sensitive. So we need lots of dishes to collect the light. We need to build a telescope that has to measure a large volume. And so we need to map out a large area on the sky. We also need to look back in time over a large range in time because we want to see the evolution of the dark energy. And we need to be very careful with how we build the telescope because the galaxy is so bright, we need to remove the signal of the galaxy. And to do so means you need to understand your telescope very well. You need to calibrate it very well. So that's the concept behind the hydrogen intensity mapping and real-time analysis experiment, or Hirax. And you can see another contrived name made up by astronomers. And so this is a concept for Hirax. Hirax is currently, in the process of being built. And the telescope will be in the Karoo Desert in South Africa. The hydrogen intensity mapping is basically mapping out galaxies in hydrogen using this intensity mapping technique. The real-time analysis part I'll come back to at the end of the talk. But let me maybe get a move on because I'm slowly running out of time. So the design for Hirax, and shown here is a single so-called satellite dish or antenna. And so we've got a 6-meter dish. It's larger than you can actually, it sounds small, but it actually fill up the room you're sitting in. And so we collect the light with these dishes, thousands of these dishes, or hundreds to start with. And then we focus that light onto what we call a receiver. And that light is then, or that signal, that radio signal is then transported over optical fiber. It's converted into an optical signal, transported to the kind of supercomputing back end, converted to a digital signal. So all the inputs from, we eventually aim to build up to 1,000 dishes. All the inputs are then coming from all these dishes, are then combined into, made into a digital signal. The frequencies they observe, shown by these different colors, are then shuffled around into groupings of the same frequencies, and then the inputs from every pair of dishes. So for 1,000 dishes, it's the square of 1,000, which is about 1,000,000. So there are about 1,000,000 combinations of pairs of dishes. Those go into this kind of supercomputing X engine, or it's made up of a number of graphical processing units. So the same, things are used in gaming. So that we've benefited from those advances. So the signal is then processed in these with this GPU supercomputer. So just looking at some of this hardware, and don't worry about the details. Here's the dish. So here's an example of a composite dish. This is actually a focal ratio 0.25 dish, but we've now made 0.21 dishes, which is our final design. These are large structures, and these dishes are very deep. This is a picture of the receiver or the feed that sits at the focal point of the dish. This is a somewhat blurry image of the transmitter system, the fiber transmitter system, and this is an image of the so-called F engine that does the digitization and channelization of the signal. And this is an image of the CHIME telescope, which has been is a telescope in Canada and has made a number of exciting discoveries. And this is their F engine, but Hirax will have something similar. And then that input then goes into the X engine for the correlation. And so this is actually Hirax's X engine. It's being developed by our partners in Switzerland. And so this is an image of it in the CERN facility, the accelerator center, where we did some testing on it. So this is real hardware that's coming together. The Hirax has a massive data challenge. I mentioned all those combinations of dishes, 1,000,000 combinations. We have in frequency, so across the band, we observe from frequency of 400 megahertz to 800 megahertz, so just below the cell phone band. We have 1,000 channels, and we're collecting data, continuously and averaging, over 10 seconds. So if we collected all the data and averaged it over 10 seconds, we would basically collect 300 terabytes a day. So that's like 300 hard drives. So that's a really challenging problem. In fact, we cannot deal with that data volume. We need to compress the data without throwing away information by a factor of a few hundred. And if you'd like, you can ask me about that in the question and answer session. But that is the idea for Hirax. And you can see that the raw data coming in is something like for the 1,000 element array, 6 terabits a second. It's comparable to the bandwidth of Africa, the data flow in and out of the continent. So it's a huge data challenge. So we've been using the Hartbeespoort Radio Astronomy Observatory to do some prototyping. So here's a prototype Hirax array. This is not the final dishes. Our final dishes are going to be made of fiberglass with a metal mesh that's embedded. But this has been a very useful site to actually do a lot of testing of the telescope. We actually are going to be based in the Peru. So here's Durban, from where most people are calling in. This is actually a image of the Vodacom coverage around the country, and you can see that in this place, in the Peru, there's very little coverage, and that's to our advantage. And by design, these cell phone signals interfere with the radio signals that we're trying to measure. So this is in the Peru, near the SKA site. And so if you zoom in here, this is the town of Carnarvon. Here is Meerkat and soon to be the SK telescope. And then on the main road today is the location of Hirax. And so this is just an image of some of the people on the project, including myself, at the site. So you can see it's very dry and very desolate, and there's nothing really happening there except radio astronomy. Other Hiraxes, so the name is suitably contrived. On the left is a Dassi, so that's its name is it's Hirax, and so these are resident also in the crew. And then we found out after naming the project that there's also a thrash metal band called Hirax, so maybe we'll invite them to play at our launch of or inauguration of the telescope. Location is very important. I mentioned radio frequency interference, cell phones disrupting the signal. So these spikes here are cell phone signals, and we actually need to dig much deeper into the data below the spikes. So you can see in this band from 400 to 800 megahertz, the site is actually very clean. So this is real data from the site, and there's not much. This is just the sky, basically the sky background. And so this is what we need to do really good astronomy or radio astronomy. And this is actually, our government has had a great kind of vision in promoting astronomy because we've got a geographical advantage. And I'm showing here a government gazette from 2008 showing that the Astronomy Geographic Advantage Act, being adopted. So we treat this area. So this is in the optical, this is Sutherland, so this is SALT, and then in the radio, this is Meerkat at the site I've just been talking about. So emissions are controlled there, light pollution is controlled. So this is really, a great place for doing astronomy, and many experiments are looking at South Africa for hosting, their experiments in these areas. So this is the Hirax team. As I mentioned, it's a big collaboration. We've got a number of local partners. So these are just the logos from all the partner institutions, but also international partners. And, there's a large number of people in the collaboration, over 100 team members. And, it's a very ambitious project. And we've got an excellent local and international participation. In terms of the science goals, I've mentioned the baryon acoustic oscillations shown here on the top left. We can also use the survey of galaxies of the hydrogen, distribution, this intensity mapping distribution to track the dark matter and cross-correlate. So this is an image of the sky. Hirax is shown in gray here, the region it will map out. It's going to map out about a third of the sky. And there are other experiments like the Rubin LSST that I mentioned will cover the same area, and other big projects like the CMB experiments like Advanced ACT and the Simons Observatory. So there'll be a lot of complementary science or correlated science we can do. But in addition to that, another exciting project or type of science we're going to do is detect lots of fast radio bursts. So a key part of our science is detecting transients, things that kind of flash in the radio sky. This slide is about measuring galaxies through their hydrogen absorption. I'm not going to talk about that. And this slide is about measuring the galaxy, the magnetic field in the galaxy by the emission I mentioned earlier, the very bright tens of Kelvin emission. So just to close up on the dark energy, and I see I should be closing up soon. This is an image of what we call the equation of state, so the ratio, the stiffness of the dark energy, and how that stiffness changes in time. So the W0 here is the stiffness, and I remember I said -1, and WA is here if it changes, that stiffness changes in time. So if it did, then we would have evidence for something that's not a cosmological constant. So if we get a measurement of WA, which is not 0, it tells us that Einstein's cosmological constant isn't the correct description. And so you can see this is a very powerful measurement, measuring it, at the sub% level. Current measurements of these parameters are shown here using the Planck satellite combined with Sloan in blue or combined with supernova in red. And the combination of all the data so far gives us the gray contour. But if you look at what Hirax can do, you can get down to the black contour. So Hirax will really advance this area in terms of constraining the properties of dark energy. So I just wanted to finish up by talking about fast radio bursts. these are millisecond, which is another exciting area that we can probe, a scientific area. These are bright flashes in the radio sky that go off, very frequently. Every second, if you could see in the radio, you'd see these bright flashes across the sky, throughout the whole day. They're very bright as the brightest sources in the sky, but they only last a millisecond. They have this characteristic signature in time and frequency, and that's how we detect them. We've detected now many hundreds, and that's thanks to the project I mentioned, the CHIME telescope. So Hirax will be similar to CHIME in that it'll measure dozens of these a day. But the big issue is because Hirax is measuring a very large area of sky, we need to know where these fast radio bursts are coming from. We can't localize them very well. There's many different models for these fast radio bursts. I'm not going to go into all of them now, but these magnetars are probably the best candidate. But it would help to know in which part of the galaxy, external galaxies, they're measured in very distant galaxies, these fast radio bursts are coming from the center of these galaxies or from the outskirts. Currently, we cannot localize them to within hundreds of galaxies. So we can't even say from which galaxy they're coming from, let alone which part of the galaxy. And so what we're going to do is, with the primary array, we're going to detect fast radio bursts. We're going to also set up outrigger stations. And currently, the one we've made most progress with is with Botswana, but we're aiming to put outriggers elsewhere around on the African continent. And that's to give us very long baselines and or separations between dishes. And when you get very long separations, you can localize things. You can measure very fine scales. And so this is showing how we can localize the fast radio burst. And with an array like this, we can go from a localization which involves here, hundreds of galaxies to from arc minutes to arc seconds, so 60 times or maybe even 100 times better. And we can localize it to this kind of spot within the galaxy. And that's going to be very important for trying to understand these fast radio bursts and how they form and how they evolve. So that's another really exciting part of the Hirax project that we're hoping to achieve with these outriggers across the African continent. And so I'll end there, and I apologize for going slightly over time, but thank you very much for listening, and I guess we can have some questions now. Tanya?
Thank you, Kavi. I really thank you very much for an exciting talk, and it sounds really like a very ambitious project. I've got some questions in the chat, and because we are short on time, I'll just read them out. And then if there is still enough time for somebody to unmute, then I will let you know. So Isaac Lundell asked, is dark energy ubiquitous in our local neighborhood? And is there any way in theory that we could interact with it experimentally? Alternatively, could it be explained away by making changes to the geometric model of space-time?
Yeah, that's a very good question, Isaac. So dark energy is also ubiquitous, but because it's very dilute, it's spread over the whole universe, it has less of an impact in our local neighborhood, in our solar system, for example. So it doesn't make up much of the energy in the solar system because there's a lot of matter in there comparably. So it really comes into play on very large scales in the universe. So when you say experimentally, I assume you mean doing a lab or tabletop experiments. There are ways people are thinking about, doing experiments in the lab to measure dark energy. But these are still in very early days, and we don't have any results from that yet. Your second question: could we explain away the dark energy by changing our model of space-time? And the answer is yes. We can actually modify our theory of gravity. That would then say that what we explain that what we are observing today in terms of the acceleration of the universe, etc., could actually just be a different version of gravity, and that's very exciting. And there's a program to try to build alternative models of gravity that can explain the dark energy, and then also to constrain using observations, or experiment or whatever you'd like, the properties of those models. So yes, maybe the dark energy is another epicycle, so to speak, but we are building alternatives and trying to test those alternatives. Isaac also asked about the radius or the diameter, 6 meters being the radius or diameter of the dish. That's the diameter of the dish, Isaac.
Okay, you want to answer Elo's question?
Yes, so the question is, does the building of these dishes and telescopes have any adverse effect on our environment? Yeah, thanks, Ela. That's a very good question. So I think there's a few aspects to this. Firstly, to construct such a telescope, we had to go through a rigorous environmental approval process. And so we will disrupt the site. This area is something like a few hundred, 200 meters by 200 meters in the Kuru. We've been careful to avoid any waterways, and we've been very rigorous also in terms of heritage impact assessment, in terms of any cultural items, in terms of any plant species, etc. We've gone through all those processes. Once we complete the experiment, we expect a lifetime of something like 10 years. We will rehabilitate the site, back to what it was. Interestingly, I would argue that the site is, well, not because of Hirax, but because of the investment in radio astronomy, the natural habitat has actually flourished since radio astronomy started in the area, because basically all the land was bought up. And because the telescopes like Meerkat only occupy a very small fraction of the land has now been given over to sandparks to manage, and it's become a national park. So a lot of the vegetation has now flourished because there's no sheep grazing on it anymore. So farming has stopped, and the natural landscape has come back. In terms of power usage, we also use a fair amount of power. So something like the full array would use 200 kilowatts. But we do plan, when we scale up to the full array for 1,000 dishes. At the moment, we're planning on building 206. To start with, we do plan to have set up a solar array, so that we will be completely reliant on solar energy. So those are the ways we've been thinking about the environment. I don't know if that fully answers your question, but you can ask more if you'd like. The next question.
If you could just briefly or whatever.
Yeah, so the question is, where are we in terms of knowing about dark energy and dark matter? So yeah, let's take dark matter. So we don't know what the dark matter is. We have physical theories for what it could be that range from anything from a very small, subatomic particle to things that are as big as planets or small stars, mini black holes, etc. Those massive objects are probably unlikely to be the dark matter. So we believe it's a small, subatomic particle. We've been trying to find evidence using accelerators like at the CERN Accelerator Center for the dark matter, but we haven't been successful in that yet. The other ways, and we are thinking about other experiments to try to detect dark matter, but that program has been unsuccessful. In terms of dark energy, we really, we don't have a very good handle or model for dark energy. The reason is because the naive expectations from building a physical theory for this vacuum energy, if it was, this cosmological constant, comes from, cancellations or in the energies of these fundamental particles. And the prediction there is something that's significantly higher than what we actually observe, many, 100 orders of magnitude larger. So the fact that the dark energy is relatively actually quite small compared to what we would predict from physical theories is very confusing, and I don't think has been explained very well. So we really kind of stuck with our models for dark energy, and I think that's why a lot of energy is going into trying to get more data on dark energy by building telescopes like Hirax, so that we can understand its properties better, and maybe that'll help us, it'll help shed some insight into what the properties of dark energy are, and therefore what it could be from a physical point of view.
Right, our time is up, but before we unmute ourselves, just an announcement. So on the 1st of November, we have another exciting talk coming up, which will be presented by Professor Ursula Schauler. This time we are coming back onto the Earth, and we are going to explore the ecology of estuarine, marine, and socioeconomic systems. So the title of her talk is Beyond the Individual, Embracing System Thinking in Nature and Socioeconomics. So don't forget to diarize the 1st of November, and we start at our normal time from 5:30 to 6:30. I would now like to also take this opportunity to thank a few people. Of course, Professor Moodley as our star guest for giving up his time to share with us his exciting new project, which I think will put South Africa quite definitely on the map of being on the forefront in astronomy. Dr. Sally Frost, who coordinated the event, and Ashok Raj, who designed the invitations and wonderful backgrounds. And now please unmute yourself and put your hands together for Professor Kavilan Moodley. Thank you very much for joining us tonight, and I hope to see you back on the 1st of November. Good night, everybody.
Bye.